Okay, so last time we left off on combustion reaction. Now, a combustion reaction in this definition is going to be a pretty narrow definition, okay? Most importantly, it's going to be a carbon-containing compound that's going to burn an oxygen gas, and that's going to form carbon dioxide and water, okay? So again, that's a very tight definition, right? Notice that you can burn metals, for example, like the magnesium flares we were talking about, and that doesn't fulfill this condition, okay? So this is very specifically a carbon-based fuel definition, right? Now there is definitions that go further than this, but it's a good definition for an entry-level class, okay? Now, one of the things that's going to be put off by this combustion reaction is going to be heat, energy. Can everybody see that energy right there? Fantastic. What is a flame, by the way? A flame. Yeah, like fire. Yeah, what is it?
Oxygen, fuel, and heat.
Yes, exactly. So what a flame actually is it's the fuel spreading over an area, reacting with the oxygen in that area, and those release heat and light at those points. And so it's over a broad area because the fuel takes a while to spread out and mix with the oxygen, okay? This is actually why, for example, you can do like blow torches and you can do spot welding and things like that, okay? All right, so when a propane heater, fireplace, or wood stove is used to burn fuel, adequate ventilation is always necessary. One of the reasons this actually becomes quite dangerous is people have a tendency to put those in places where the oxygen flow would be hindered, right? For example, in like a log cabin or in a boiler room, right? And so when the oxygen supply is limited, you get a limiting reactant, don't you? And that limiting reactant is oxygen. So the oxygen doesn't get used as much. And what ends up happening is you can produce then what's called carbon monoxide. This can also happen in your engine block if it's not getting enough oxygen at certain points. This is actually one of the reasons you have the catalytic converter. It actually reacts away the rest of the carbon monoxide that might get generated, okay? You don't do that typically on a heating system like a stove because it just is mixing the fuel up in the air, right? Doesn't have a pipe to bring it away. So the carbon monoxide, on the other hand, is a poisonous, odorless gas. This is actually the reaction. It still produces heat, still produces water, but instead of producing CO2, which is the more oxidized form, which is mostly benign. As far as possible poisons go, carbon dioxide is about as benign as you can get, actually. Okay. In fact, oxygen would be a more dangerous gas than CO2. Yeah. All right. So here's carbon monoxide. Again, it's colorless, it's odorless, it's a poisonous gas. It actually binds to your hemoglobin in your red blood cells. This bound hemoglobin can no longer carry oxygen as long as the carbon monoxide is bound. The carbon monoxide actually binds better than the oxygens to your hemoglobin. And so to get rid of that carbon monoxide, you usually have to put a gas mask on somebody or have them breathe a lot of oxygen over a period of time, okay? What this means is that if you are poisoned with carbon monoxide gas, you're not going to be okay by just stopping the carbon monoxide gas. Whereas if you were CO2 and you started being short of breath, as long as you can get more oxygen, you'll be fine, okay? So if you just open the room, open the containment that's causing you to have a buildup of CO2, you'll be fine. Carbon monoxide is not so. It actually takes a pretty extended period of time for it to release, okay? And so what you normally need to do is they would come in with oxygen masks, put the oxygen masks on the people, and then give them far more oxygen than you'd normally be able to give in a normal setting like here, where you're just breathing normally. So, again, it's not going to allow O2 to reach your cells. Yes, definitely. This is going to cause a person to experience a reduction in exercise capability, visual perception, manual dexterity. Has anybody ever felt lightheaded? Anybody gotten to the point where they're near pass out? Yeah? Okay. You get a little loopy, right? This is actually the biggest danger of things like carbon monoxide poisoning, is that your thinking ability actually goes down first. And so when you start experiencing the poison, you get lethargic, you don't want to move around, you don't want to get out of the area, and your thinking ability goes down drastically. And that's actually the most dangerous part of it. Okay? That's why if people don't catch it early, they usually end up dying. Anybody ever heard of the canary in the coal mine? Yeah? Okay. So, similar phenomenon. Sometimes it is carbon monoxide, actually, but sometimes it's also methane. And again, it's the shortness of breath.
Is this stuff like underground, right? Something else.
So it can be underground, especially in volcanic regions. Okay. Especially like one of the reasons that you'd end up with carbon monoxide poisoning in mine shafts would actually be the machinery. So you don't have enough oxygen to burn the fuel fully, and so you end up with buildup of carbon monoxide. But yeah, usually it's a mixture of methane and carbon monoxide that becomes the issues whenever you're underground. And then the canary was actually just a more sensitive, lighter weight creature that would pass out first from the poisoning. And so by the time the canary passes out, you know, oh yeah, I need to get out of here. Okay. All right, so hemoglobin, again, that's the protein in the blood that transports O2 to the cells. Everybody's aware of hemoglobin, has heard of that before. No? Okay, it's what makes your blood red. It's the protein that carries oxygen in your blood. And one of the common misconceptions, if you've heard of hemoglobin, do you think it carries CO2 back to your lungs? Very, very common misconception. It makes its way into a fair number of biology textbooks. It does not. CO2 is actually transported in your blood as an acid, carbamic acid. Yeah. And there's an enzyme that converts it to and from carbamic acid millions of times a second. It's very fast. So, anyways. These are what happens when you have the carbon monoxide attaching to your hemoglobin. So at 10% of your hemoglobin spots filled up, a person's going to experience shortness of breath, mild headaches, drowsiness. This is usually why people end up sort of misidentifying it, is because they're either not, moving around, or they're moving around and going, I'm just a little short of breath today. And then they get this mild drowsiness, and they get a little bit lethargic, and it doesn't matter.
Where are people getting this from?
Huh?
Where are people getting this from, like carbon monoxide poisoning?
Mostly it's from like gas stoves and water heaters now. That's the most common source of carbon monoxide poisoning. It's fairly common, especially in countries like China, Africa, Southeast Asia, where there's not as many like safety guidelines. And there's ways of designing stoves so that it's less likely to have carbon monoxide buildup in your house. And many countries don't really do that. Okay. Yeah. Also, some countries use wood as a fuel. That's another big one. Basically, anytime you burn fuel in an oxygen limiting condition, like this room doesn't have particularly great airflow, right? If we were to have a wood stove in here, it's very likely we'd have carbon monoxide buildup. Yeah. Now you can get detectors very cheap. They cost about $5 on Amazon. Okay. So if you do have one of those, I recommend a carbon monoxide detector. Yeah, they'll also get one that's a methane and carbon monoxide detector, or natural gas and carbon monoxide, and you'll be fully protected. It'll be good. It'll go off and it'll be like, oh shit, that's why I'm drowsy. Open the windows.
We have one at the house that's gone off before. Yeah, ours has gone off in our house before, so my dad just took out the batteries and put it in the drawer.
Oh wow.
That's our old house.
Oh, wow. Now, a lot of the fire alarms are actually like triple purpose ones that do carbon monoxide, methane, and fire alarm. Yeah. That's funny. Oh, yeah. Yeah. So, 30%, a person may experience more severe symptoms. This will include things like dizziness, mental confusion, severe headache, and nausea. By the way, the "I'm fine" part of the sentence is actually very disturbing. The reason that it's disturbing is that the mental impairment and drowsiness is one of the first things that happens. And so, like, people feel okay and actually feel euphoric. You know people do that, right? Paint huffing and such, because it makes you feel euphoric. You guys weren't aware of that? You've never heard of that? Anyways. So if you ever do suspect that there's carbon monoxide poisoning or methane poisoning is just lightheadedness as well.
Lightheaded my first thought and I didn't eat enough that day.
Yeah.
Not like I'm
I'm
poisoned.
always lightheaded and
Maybe not. Maybe you're anemic though. Get some iron.
I got tested.
Yeah. 50%, a person's going to become unconscious and die if not treated immediately with oxygen. And this one is one of those where you actually will die if you don't get treatment. Okay? And that's because the carbon monoxide is actually binding to your hemoglobin. Okay? Like methane, you won't actually die, or CO2, you won't actually die necessarily from going unconscious. Okay? You just need somebody to open windows and you'll come back normally. Okay? Carbon monoxide, opening a window is not going to do it. Yeah. You need to seek help. Okay? All right. So these are the summary of your reaction types. Everybody good with those so far? Okay, fantastic. There is a semi-memorization component to this, but again, it is not something that needs to be perfectly memorized. Did you guys hear Goldfish is changing its name and test locations? Is it fake? It went into several news. If it's a fake, then they tricked news outlets. They're trying to rebrand themselves to be upscale.
So they're calling themselves Tulane Seabass?
Yeah.
No child is gonna want to eat.
No, they're trying to get adults to do it.
Like goldfish is not meant to be like an upscale, like.
No.
Yeah, I know.
It's silly.
I'll be 8 years old.
So let's identify each reaction as combination, decomposition, combustion, single replacement, or double replacement. So what's this first one? Single, very good. What's this one? Double replacement, very good. What's this one? Okay, we're not agreeing. Kinda. Okay. What do you think this one is then? That one's combustion, yeah. Very good. Okay. And the one that people were... Oh, I actually have a different one here. Wow. Okay. Yeah. So this one right here, this would be a single replacement or an oxidation reduction reaction. Okay. In case you're wondering, that's also a redox reaction. This one right here, that's a combination reaction. Okay. And can you tell the difference between combination and single replacements? Yeah, it combines something more complex. Okay. Okay. This one right here, what's that one? That's a combination. This one over here? Very good. This one? Carbon, oxygen, CO2 to water. Yeah, combustion. Yeah. How about this one? Okay. Yep, you got it. By the way, one of the big key, like, telling hints on these double replacement reactions is they're almost always salts. Okay? It's very, very common for them to be salts, and that's because they have a cation-anion pair that can then swap easily. Okay? So if it's two salts being mixed together, especially if they're aqueous, and then goes solid, very, very common. It's like the prototypical double replacement reaction. Often called a metathesis reaction instead. How about that one there? Yeah, decomposition, right? It's going from something more complex to something less complex, right? Okay. Very good. Okay. In case you want to join the QR, that's just the Q&A QR. So if you end up shooting off a, hey, I didn't understand this part, that'll come up there. Okay, so oxidation reduction reactions. This right here is rust. Everybody hopefully is familiar with rust. Okay, it happens around us all the time, doesn't it? All right. And rust is iron reacting with the oxygen in the atmosphere. Interestingly enough, it actually typically reacts with the hydroxide free radical in the atmosphere to start the process, but it can react with the oxygen as well. An oxidation reduction reaction is going to provide us with energy from food. That's actually how we digest things. Many of you are probably digesting various forms of food right now. Provides electrical energy in batteries. Redox reactions are the primary methodology of batteries, actually. There are other types of batteries you can make, but the ones you're using are basically all redox reaction ones. Okay? This is going to occur when iron rusts, of course. This right here is actually iron rusting. That's one of the possible reactions that produces rust. It's the most common one. Okay. This one right here is an oxidation reduction reaction. Why do I say both of them? Have you guys ever heard of an oxidation or a reduction? Have you ever heard the term oxidized? Okay. So oxidized was an oxidation reaction happened. Okay, that's actually what that word means. And if I have something taking something, what else do I have to have? I have to have something. Yeah, I have to have a loss to get a gain, don't I? And vice versa. To get a gain, I have to have a loss. And so when we talk about oxidation reduction reactions, if an oxidation occurs, that means a reduction has to have occurred as well. Okay? When we have a reduction, that means an oxidation has to have occurred. So they are paired. You have to have one to get the other. Now, the oxidation, this is actually going to be the loss of an electron. And so something has taken an electron from that. That is an oxidation. That's why oxidized. Something has taken an electron there. Reduction is going to be the gain of electrons. So when you're reduced, you gain a negative charge. Now there is a abbreviation for this, oil rig. Oxidation is loss of an electron. Reduction is gain of electron. I don't actually think it helps a lot. In fact, every study I've seen done indicates the songs and these combination of the letters typically do not help. But if you would have been able to memorize it just by repeating it 5 times, you also would end up memorizing it from this. And that's basically it. But anyways, if it works for you, go for it. I'm fine with it. I personally remember reduction is gaining negatives. Electrons are negatives, and so you were reduced by gaining a negative, aren't you? Oxidation is the loss of an electron. Oxygen typically does the oxidations and takes electrons from things. Okay? Anyways, feel free, oil rig, you can do a song, you can remember that reductions are gaining negative charges. Any which way works for you. Okay, so this right here, the Statue of Liberty, what color should she be? Yeah, it's It's actually would have been more of a gold color, but yeah, it's a copper alloy. Okay, she should be a copper alloy, more of a brass gold color. Okay, why is she green?
Oxidation.
Oxidation, yeah. The copper has been oxidized, and for whatever reason, the people of New York protested when they were trying to restore the statue to its original gold. They liked the green. So, it's kind of like the French or the Romans. Do you know what color the white pillars should be? They shouldn't be white, yeah. They would have been painted, and it was a misunderstanding of the culture hundreds of years later where the paint had, come off. Yeah. Anyways, and that's why the front of your school looks like that. They shouldn't be white pillars. And the White House is white because they misunderstood the culture. But anyways, so this right here is actually an oxidation reduction occurring. Here we have this blue solution here. Everybody good with that? That's actually copper 2+ in the solution, causing that nice blue color. And so we're going to throw a zinc metal in there. When we put that in there, what's going to happen is the zinc is going to lose electrons, the copper is going to gain the electrons. It's an oxidation and reduction, right? And that's actually going to pull these blue metal ions out of the liquid here. If you were to look very closely, and the color palette was actually reasonable on this thing, you would see a very slight drop in the blue colors. Okay. Anyways, you can see the copper plated out on that metal right there. So, there you go. Okay, so let's go ahead and identify each of the following as an oxidation or reduction. I split the reactions up into two halves. So over here we have a metal. It is then going to product where it has lost the electrons, hasn't it? Is that an oxidation or a reduction? An oxidation. Here we have a positive metal, don't we? We have a cation. It is gaining electrons, isn't it? So that is a reduction. Got it. Here we have a neutral Cl. It has went to a negative Cl. What is that? It's reduction. Yeah. The other way of looking at that is it's gained electrons right there, isn't it? Okay. If you have the electrons listed out, you can actually just go to the reactants versus the products. If it's on the reactant side, that is gaining. If it's on the product side, that is losing. Okay. The other way also is to look at the charges. So if the charge goes down, it is reduced. If the charge goes up, it is oxidized. Okay? That's why I personally prefer the gaining negatives is reduced, going down in charge is reduced, because it actually encompasses everything that could happen. Yeah. So, okay, let's go ahead and try this. In light-sensitive sunglasses, like mine in here, the UV light initiates an oxidation-reduction reaction. So when we're exposed to UV light, we have the silver ion and chloride ion that's then going to undergo a reaction and produce silver and Cl2, which is chloride gas. Okay? So which reactant would be oxidized? Which reactant is going to be reduced? I'm going to give you options in a bit. Okay. So figure out which reactant is going to be oxidized, which reactant will be reduced. Which one gets more positive? Which one gets more negative? All right, I'm going to put the quiz up so you can join. And then I'll give you a list of options. And you have to figure out which one. By the way, oxidation is normally referred to as OX for the abbreviation. Reduction is normally referred to as RED. Together, you can call it redox reaction. REDOX. Okay. Ready? Set. There's no timer. And so the oxidized species goes first, the reduced species goes second.
It's asking for a code.
Yeah, you can put in the number to get to it too. All right, folks, go ahead and put an answer in. I'm going to go on now. Okay, so we got pretty equal, actually. Okay, so there's only two species. It can't be both, okay? It is. Chlorine is the one that's actually oxidized. Silver is actually the one that's reduced. So again, the silver is going from a positive to a neutral. See how that doesn't have any charge up here? Okay. So that one's going from positive to neutral. It's gaining a negative charge. That means that that one's reduced. Okay. We look over here to Cl minus, and that was negative. Over here, it doesn't have any charge because those are two Cl's. Neither one could take the electron from the other. And so it's going from a negative to a 0. That is more positive, isn't it? And so that one's being oxidized. All right. So let's talk about oxidation reduction in biological systems. Now, because of the limitations in biological systems, that they're always happening in water, that they're commonly going to be using hydrogen and oxygens as the primary oxidation reduction mechanisms, there's actually some shortcuts we can use when we're talking about biological systems, okay? And you'll actually catch, once you get into some biology classes, if you haven't already, they use these shortcuts a lot. They basically talk about oxidation reduction as if these shortcuts are the only thing that exist, okay? And that's because in biology it kind of is. So right here, if you gain hydrogens, what you're seeing is a reduction, okay? And that's because hydrogens don't hold on to electrons very well. So if you see hydrogens added to something, that's going to be a reduction. If you gain oxygens, that's going to be an oxidation because the oxygens are going to pull stuff away. Okay? So right here we actually see two hydrogens that were attached to a biological molecule. It's going to react with coenzyme FAD. Has anybody heard of coenzyme FAD before? How about NADH or NAD+? Know those? Okay. The NAD+ would be the equivalent of FAD. Okay, it's the other one that's used commonly in biological reactions. So FAD, NAD+, these are the primary oxidation methods in the body, okay? All right, and so we're going to transfer hydrogens to this coenzyme FAD, going to coenzyme FADH2. That right there is a reduction. We're actually doing two reductions on it. And over here, we're actually having an oxidation, which is the loss of the hydrogens. All right. And correctly speaking, it's actually the gain or loss of electrons. That is the oxidation reduction. But when we're looking at biology, gaining and losing hydrogens is the same thing. Okay? So if we're gaining hydrogens, it's just as if you gained electrons. All right, so this is actually an example of a pathway. This would be methyl alcohol here. Anybody know what methyl alcohol is? This is wood grain alcohol. Okay, so this would be the alcohol that they, during the Prohibition, the mob served a bunch of people and killed them. Okay, this is the alcohol that they go, if you drink moonshine, you're gonna go blind. You ever heard that? No? So if you don't do a proper job distilling moonshine, you can get methyl alcohol over in the finished product, and that can cause you blindness and death. Okay? Not that the regular alcohol that you drink can't cause death as well, but methyl alcohol takes less. Okay? All right. So methyl alcohol is going to go to formaldehyde in the body. And anybody ever heard of formaldehyde before? Yeah, there are some glues that have formaldehyde in them. It's fairly unusual. The formaldehyde would typically be like preserving corpses. Yeah. And that's what you'd see. They use it, at least they used to, they use formalin more now, but which is a form of formaldehyde. But for like a mortuary. Okay. Did I ever talk about the puffy red eyes of a mortuary? Yeah. That's formaldehyde poisoning. Okay, so formaldehyde is going to go to formic acid. Anybody know what formic acid is? Anybody ever seen the Asian beetles or ladybugs? Yeah? Okay. Anybody gotten bitten by them?
I think so.
Yeah.
I think I have.
Gets on you. It actually sprays formic acid on you. Yeah. Yeah, and so formic acid is the defense mechanism of a fair number of insects. They spray the formic acid out on you. It actually tans your flesh, like tanned leather. So I imagine this, you drank methyl alcohol in your liver. You're then going to do these oxidations to try to get rid of it. It's going to go to formaldehyde, which is not great for you. But worse, it goes from formaldehyde to formic acid, which actually tans the flesh of your leather and damages it quite a bit.
How much methyl alcohol is made to like toast?
Usually like a couple shots.
No, but
Yeah, like a couple shots worth.
this is just nothing.
No, it's not much.
Isn't
No.
formaldehyde like? I thought it was in like the bug insect deodorant stuff. And it would
Not
cause
normally.
cancer or something.
So formaldehyde, it probably is a carcinogen. I haven't looked, but so I'd have to look again whether it's a suspected carcinogen or a confirmed one.
It was in, there was a big thing with Ben and Jerry's where it was found, there was like trace
I could
amounts
believe
of
that.
formaldehyde.
I could definitely believe
It
that.
was like, if you ate 30 million pints of it, the formaldehyde would kill you.
Yeah. Oh yeah, it is poisonous gas, and a poisonous fluid if you get it in fluid form. You don't want to drink formaldehyde; it would poison you.
It says certain products containing formaldehyde are considered pesticides under federal law. So.
I have never seen a pesticide use
Because I remember
formaldehyde.
my dad spraying like insect repellent in the
Weird.
house, and then like a couple days later, it was on the news that it was like a carcinogen or something. It was like it caused
Wow.
cancer.
So I'd actually have to look. Is it a possible carcinogen or is it a confirmed? Because there's a lot of stuff that's possible carcinogens. For example, trees. Trees are listed as possible carcinogens. Yeah, that's why in California you actually have to have a plaque on anything that's possible carcinogen, and some people get crazy and put plaques on trees.
The World Health Organization has concluded that formaldehyde is carcinogenic to humans.
Okay, that doesn't really mean anything.
Yeah, I know. It doesn't say anything. about
Yeah.
if it's confirmed or not.
I'll look up the SDS if you remind me sometime. I can tell you. Yeah. Okay, anyways, we make formic acid. The reason your body's making the formic acid is it would then be further oxidized to CO2. And then you can breathe the CO2 out eventually, right? And so that's basically how you try to get rid of things. These intermediates are toxic. They typically cause headaches, possible death, because they're going to interfere with key functions of the cell. The formic acid is a really nasty one. It very easily does permanent damage. And that's because it actually will tan the flesh around that area. Okay? And so it damages your liver. So don't drink methyl alcohol. No matter how desperate you are. That's a bad idea. Anyways, so when you have an oxidation, they're going to involve the loss of electrons. That's always the correct definition for an oxidation. That is the proper definition for an oxidation. In biology, you can oftentimes use the addition of oxygen or the loss of hydrogen atoms to help you keep track of what's being oxidized. The reductions are always going to involve the gaining of electrons. Now, you can also see this in biology settings as the loss of oxygen or the gaining of hydrogen, primarily because you don't have anything more electronegative than the oxygens in biological systems. Yeah. All right, so let's talk about mole relationships. Right here we have iron reacting with sulfur. This is producing iron 3 sulfide here. Anybody recognize that at all? No, anybody ever been to a hot spring? It has this like kind of rainbow pattern brownish color that builds up around the hot spring area. That's that. That's the iron sulfide. There's another form of iron sulfide. This is not iron 3 sulfide. That is called fool's gold. Anybody ever seen that one before? Yeah. Okay, so this is the law of conservation of mass. It's going to indicate that in an ordinary chemical reaction, matter cannot be created or destroyed. There's going to be no change in the total mass. The mass of the products has to equal the mass of the reactants. The only time this would not be true is in a nuclear reaction, right? In that case, you actually do change mass. Yeah, you actually use some of the mass to make energy. Okay. All right, so let's talk about reaction. If we put in 215.8 plus 32.1 grams of silver and sulfur into this reaction, and we completely react everything away, how much of the products are we going to get? The same mass, right? Okay, and so we just add those masses up, and that would give us our mass for our products. This right here would actually be the reaction or the chemical equation for this reaction. What do we notice about this reaction? Is the mass of the sulfur equal to the mass of the products? Can that be true? No, they're very different, aren't they? Yeah. The mass of the silver can't be equal to the mass of the products. The mass of the sulfur can't be equal. So the mass of the reactants combined would be equal to the mass of the products combined, right? Yeah. It actually cannot be true that one of the reactants alone would be equal mass. Okay? Very, very common mistake for students to make, by the way. They'll try to take the mass of one of the reactants and restate it as the mass of the product. Okay? That actually can never be true. All right? So it's very, very, it'd be very difficult to have that. That would mean no change occurs, right? Which is not a reaction. So what is true, though, is that this equation actually gives you a recipe, doesn't it? Or a list of ingredients that have to combine to give you a product. So everybody good with that? So if we have 2 atoms of silver, how many atoms of product do we have? We have to have 1. See that? For every 2 atoms of silver, we get 1 atom of our product, don't we? Everybody said okay? Fantastic. How about the sulfurs? If we have 2 atoms of sulfur, how many atoms of product do we get? 2, exactly. Okay, now let's say that I wanted 48 eggs. How many cartons of eggs do I need? 12 dozen. A dozen carton. 4. Yeah. So I can do the same sort of math with cartons, can't I? I don't have to do it with individual eggs. I don't have to do it with individual items, right? So I've given you a collection of atoms. It's called a mole, right? So if I have 1 mole of sulfur, how many moles of product do I have? 1. Same number of moles, right? Because remember, moles are representations of atoms, aren't they? Okay. All right. So again, remember that we can use moles in these equations. So again, 2 moles of iron plus 3 moles of sulfur here are going to give us 1 mole of the iron sulfide that we talked about before. Or 2 mole, yeah, 1 mole. Can anybody Is anybody having any issues with that?
Yes.
Okay.
So like, if a mole is an exact number, then how is it not gonna be 5 moles of iron?
That's because what you're getting here is there's 2 of these for every one of the total.
Oh,
Okay. It's kind of like a double cheeseburger. There's only 1 double cheeseburger, even though there's 2 patties, right? That making sense? Okay. So this ratio is actually called the mole ratio or the mole to mole factor. Your book uses mole to mole factor. It's actually the only book I've ever seen that uses that, but we'll use that because the book uses that, okay? And hopefully that won't confuse people. All right, so the mole to mole factor, this is going to be the ratio of your moles in a chemical reaction, okay? It's kind of like the ratio you would do if you were trying to bake cakes. How many cups of flour do you need, right? Same sort of thing. And it's the same sort of math. These right here are the ratios. What do you notice about ratios? You can flip them upside down, right? So that you can get into whichever one you want to be in. Okay. Okay, so let's consider this following equation, and let's get the mole to mole ratio or mole to mole factor of the H2 and N2. So we're trying to go for H2 and N2, right? Which of these would be the correct mole to mole factor? So we look at N2. We look at this number here, right? That number is what? Yeah, there'd be 1 N2. So that's 1. And then we're trying to regard that with regards to hydrogen, right? And so, how many hydrogens? 3. So there, for every 1 mole of N2, we would have how many moles of hydrogen? 3. Yeah, and that's the mole to mole ratio, isn't it?
So you won't have to look at the product side for that?
You may. We'll do one with the products, this next one actually. Okay. But you can do it for any combination in the equation. So if they ask you for 2 reactants, like this one, yeah, you don't have to look at the products. Yeah, you just look at the one you're trying to figure out at the time. It would be like saying, I'm trying to bake cakes. I have 4 cups of flour. How many cups of sugar do I need for that? Yeah. Yeah. Is that making sense? Okay. Okay. Okay, so mole to mole factor for NH3 and H2. Yeah, 2 NH3s for every, how many H2s? 3. Very good. Yep. And so it is 2 again. You got it. Okay. Very good. So how many moles of Fe2O3 can form from 6 moles of O2? We just set up that mole to mole factor again, right? Okay. We want to get into Fe2O3, so we put that on top, don't we? We want to get out of O2, so we put that on bottom. And then we multiply that by our 6 moles we were given of O2, right? Note if you set the equations up like this, if you're tired, you can just go through and cancel units, can't you? Just like the conversions we did before. All right, so again, yep, we get 4 moles of Fe2O3. Very good. Okay, so the next thing we're going to do here, did I get logged out? Oh, great. That's weird. Huh. Weird. Actually got kicked down my slideshow. All right. So how many moles of Fe are going to be needed for the reaction of 12 moles of O2? Okay. So we need to set up a ratio, right? Everybody got that reaction? You'll need to write that down because we'll need that for the quiz. So make sure you get this reaction that you can use it. So we're going to take 12 moles of O2 and figure out how many moles of Fe do I need. By the way, the next slideshow, I'll be able to put pictures in. I broke down and paid for the damn thing. So I could put pictures into it. The $7 a month. All right, everybody ready? So how many moles of Fe are needed for this reaction of 12 moles of O2? All right, so let's go ahead and get going. You're not sure, that's okay. Answer like something you think's probably wrong. So I know that I need to cover it more, okay? That's what these are for, actually. So I know if you guys are getting it or not. And it's easy to get it when you're just following along, right? It's hard to get it when you gotta do it yourself. Okay, I'm gonna go ahead and go forward. Everybody answered? Okay, let's go. All right, so 87%, and that is correct.
Yes.
Yeah. Oh, was it? Okay, so what we're gonna do here is we wanna be in O2, right? So we have 12 moles of O2. We wanna get out of O2. We wanna be in Fe, which is what we were asked for. Everybody good with that so far? What do we have? What do we need? How do we get there, right? Okay, so we have 12 moles of O2. We want to go to the moles of Fe. To do that, we're going to have to set up a mole-to-mole ratio. What's the mole-to-mole ratio here? So there's 3 O2s, right? And how many Fe's are there to that? 4. All right. And so we're going to multiply the 12 O2 times that 4 Fe over 3 O2s. That will cancel the O2s, leaving us in our answer. Okay. All right. So again, that is 12 moles of O2. That's times 4 divided by 3. That will get us out of moles of O2 into moles of Fe. And that would be 16. Okay, so anybody ever seen welding? Yeah? If not in person, at least on like TV or online or something? Okay. Okay. By the way, anybody know why the welder has to wear all that equipment? Is it the sparks? No, they could just wear glasses if it's sparks, right? Yeah, so what actually happens is this is such intense heat and light that they get essentially a very, very bad sunburn. Yeah. And if they don't wear shielded eye protection and protection covering all of their skin, then they'll get essentially very, very bad sunburn over and over and over. Over a long time, that'll cause permanent damage. Yeah, they actually do get a kind of tan. It's called welder's tan. And it feels like your eyelids have been sunburned really badly if you do this with improper protection. Yeah. People do. What they do oftentimes is say, if you don't have the mask and stuff, a lot of people will just take your phone camera and then like put a shield around it. Weld through the phone camera. It's really stupid and really weird. Yeah. Anyways, the mask does not cost that much. Get a mask if you're gonna weld. Okay. Wear a long sleeve shirt. Wear gloves. It'll help you out in the long term. Yeah. So let's write out a balanced equation. One of the reasons that this is involving this is because why do we get such a hot flame with that acetylene gas. Anybody ever seen the welding torch when they're first setting it up? They turn it on, they light the fire, it's a big plume, right? And then they dial it in, and it gets to be a real thin, looking almost like a laser, right? Okay. That actually is adjusting the amount of fuel versus oxygen. That's what they're actually doing, okay? So they're actually trying to maximize where they have the exact ratio of fuel to oxygen that gives them the complete reaction, a balanced reaction. Okay? So like you, they're actually balancing the reaction. Ooh, ah. They're just doing it physically. Okay, so what we're going to be doing here is we're going to be balancing reactions, then we're going to be taking the amount of oxygen, the amount of one of the reactants, and we're going to figure out how much products we need, or vice versa. Now, you may have noticed that I have given you the pieces to do this, okay? I have given you a way from going from grams to moles of a substance, haven't I? That was that molar mass, okay? And then if we're in moles of one substance, then what does that chemical reaction tell us? It tells us the ratio to every other substance in the reaction, doesn't it? All right? And so we can go from moles to any other moles in the reaction, can't we? And then once we're in moles of that other, say the products, we can go back into grams by using that molar mass of that substance. Mm-hmm.
I was going to say, this is what we were doing at lab, and I was really confused.
Yes. Yeah, you guys got a little bit ahead because the course wasn't exactly... I can't design a course that both does the college.
I thought I just
Which-
wasn't paying attention or something, because I did not
No.
know what was going on.
It's the week and a half you guys have off compared to the college. Yeah. It's not really possible to design time frames that match both. Yeah. Yeah. No. That was that. Okay. So let's go ahead and suppose we're determining the mass, which would be grams, right, of NH3 that can be produced from 32 grams of N2 in this equation right here. So we're trying to figure out the mass of product we would get, right? We have the mass right here. Can we just take that 32 grams and that's how much we get of this? No, that can't be true, right? Because we're gaining hydrogens. It has to actually be more mass, doesn't it? Okay, so how do we go about this then?
Isn't the periodic table, you can use the molar mass?
You can. You got it. So we can't go from one to another with mass here, can we? So we got to get into moles. And to get into moles, we can use the periodic table, use that molar mass, get into moles of the N2. So we're going to want moles of N2 at some point, right? And we're going to want to use that ratio, mole to mole ratio, to get into the NH3. We'll be in moles at first. And then we're going to use the molar mass to get into grams, right? Okay. Let me go ahead and put nice colorful arrows in that place. So we're going to go from grams of N2, which we're given right here. We'll use the molar mass of N2 to go into moles. We're then going to take the mole to mole factor or ratio and go into moles of NH3, which is the product we want. And then we're going to use the molar mass of NH3 to go into grams. Okay? Now, I would definitely recommend doing this problem in stages. Right? Anything that you go over about 2 or 3 steps in, you really want to do in stages. Okay? Take simple, easy steps. Now, when we're going to do this, we need a molar mass, we need a mole to mole factor, and then we need a molar mass of NH3, don't we? All right. So let's get those together first. What would be the molar mole factor here? That's going to be easiest to get with this equation, right? Okay, so we need the moles of N2, right? This needs to be related to the moles of NH3, doesn't it? Okay. Now, how many NH3s are there for each N2? We look up at this equation here. There's a 2 in front of the NH3, right? So we put 2 in front of that. There's a 1 in front of this one, isn't there? So we put a 1 here. Okay? That's the multiple factor. All right, now, the next step, that's this, by the way. The next step is I need those molar masses off the periodic table, don't I? Okay, so what's the molar mass for N2? Yeah, it's going to be that 14.01 off the periodic table, right? Times 2. And that will give us 28.02. That number is in grams per mole. Okay? So 28.02 grams of N2 for every 1 mole of N2. Okay. Okay, the next thing I'm going to do is I'm going to go ahead and get that molar mass for the NH3 as well. This will give me all the pieces I need when I do my math later, right? All right, so what's the molar mass for NH3? So the nitrogen was what? 14.01-ish? Okay. And then that's plus the hydrogens, right? Right. Yep. Plus 3 times 1.0007. All right. And that's going to give me my 17.04 grams of NH3 for every 1 mole of NH3, right? Okay. Okay, so whenever I do these math problems, this is just a conversion, isn't it? So I'm going to start in 32 grams of N2, which I get from right there. Okay. Everybody good with that step so far? I'm just rewriting it. Okay, so I need to get out of grams of N2 into moles of N2, don't I? So I'm going to put my molar mass down here, 28.02 grams of N2, and I'm going to put moles of N2 on top. And that's 1 mole of N2 goes into. Notice my grams will cancel, and I'll be left in moles of N2, won't I? Okay. Okay, remember to write your units, express your units so you can keep track, okay? All right, so we're in moles now. We can now use the multiple ratio to get into moles of NH3, right? All right. So my multiple ratio, I want to go out of moles of N2. I'm going to put moles of N2 on bottom, aren't I? And then I want to get into moles of NH3. That goes on top. All right. And so 2 moles of NH3 to 1 mole of N2. That's my multiple ratio I'm going to use. Moles of N2 cancels. This is going to give me moles of NH3 at this point. Okay? All right, so the next thing I need to do is I did not want moles of NH3 at the end of this problem, do I? I want grams. So I'm going to take that molar mass of NH3. Grams are going to be on top because that's what I want to end up in. And moles are going to be on bottom. Moles of NH3 is going to cancel, going into grams of NH3. All right. This gives me 39 grams of NH3 at the end of this, because I took 32 divided by 28 times 2, then times 17.03, right? Okay. And that gives me 39 grams of NH3. Anybody have any questions? Okay. Guess what I'm going to do to you? We're going to do this. Okay, you'll need the stuff on this page here. Because this quiz was written before I had the ability to put pictures in. So, this is the part you'll need. All right. Okay, I'm going to go on to the quiz. So how how many grams of O2 are needed to produce 45.8 grams of Fe2O3 in the following reaction? That was that reaction from before. Anybody missing the reaction? Okay. Okay. Everybody got the reaction now? Okay. So make sure you draw that out so I can be back on the page where it has people's ability to join the quiz and answer. Okay. So, how many grams of O2? Keep in mind, this really is just same conversion factors we've been talking about before. You can do it the same way. I've just given you a few new conversion factors, right? Folks, anybody still making good progress? Okay, okay. Okay, I'm gonna go ahead and get moving onwards. No? Okay. I'll give you another minute.
Oh my god.
Alright. So, go ahead and guess if you didn't get anything. Okay. Don't worry, I'll go back through it and we'll solve it together. Alright. Okay, folks, gonna move on. Please put in whatever answers you got. Or something if you don't have an answer. Okay. Alright. What the hell? Okay. And my program crashed. That is just fantastic. Okay. That is correct.
Can you show me how you got there?
I am. Yeah. Definitely. Okay, so right here we have the formula. So remember that whenever you see these reactions, there are equations, right? And so we have here, how many grams of O2 do we need? That's what we want to end up in, right? We have here 45.8 grams of Fe2O3. That's what we're going to start with right there. Okay, so there's 3 parts we're going to need for this. We're going to need the molar mass of this right here. We're going to need the molar mass of O2. And we're going to end up needing the mole to mole ratio. Okay? Or another way of saying that is we're going to go from grams to moles of this. We're then going to use moles to moles to go from here to here. And then we're going to be using the grams to mole molar mass again to get into our final answer. All right. And right there is it put in one line with colorful arrows. Okay. So the next part we need to do is we need to go ahead and get on that periodic table and get the molar masses, right? So we look at our periodic table. We add 2 irons to 3 oxygens. That's going to give us 159.7 grams. Anybody have difficulty doing that? Okay. Okay, so that right there is the molar mass of the Fe2O3. The next thing we're going to go ahead and do is I'm on the periodic table, so I'm going to look up nitrogen, right? And so you're going to take the nitrogen. This is going to be, I'm sorry, oxygen. I have the wrong thing here. I didn't change from previous one. We'll do that in just a bit. So I'm going to look up oxygen, excuse me. And that is what on the periodic table? 15.999. It's going to be times what? 2. Yeah. Because it's O2, right? So there's 2 oxygens in there, O2. I'm going to multiply that number from the periodic table by 2. That's going to give me 32.00 when I end up rounding it. Okay, so the next thing I need here is I need the mole to mole ratio. So I look on my reaction here, and I want to get out of Fe2O3. So Fe2O3, and get out the number of moles of that. And then I'm going to go into O2. So I'm going to go into moles of O2.
Sorry, after you take the molar mass of the Fe2O3, it would be 1 mole of Fe2O3 over that mass?
Yeah, yeah. That molar mass is always for a single mole of that.
Okay, and then it'd be 3 moles of O2 over 1.
This should be the number you'd end up with normally, right here. So you would take the numbers off the periodic table. Those numbers are in grams per mole. Okay? And so you'd take, what's the mass of Fe? 55.9 times 2. And then that's plus 3 times 15.999.
Yeah, and that's the mass of Fe2O3, and there's 1 mole.
Yeah.
But then the next step, it would be moles of O2 over Fe2O3, right?
Okay. So right now I'm just getting together my molar masses and my mole to mole ratio. And the reason I'm doing that is because it's going to be easier to assemble those later than it is to try to do all the steps every single time all at once, right? That's how I'm going to mess up things. So when you're trying to do these problems, it's always much easier to assemble your molar masses first, because you're going to have to do additions, and then use them. Okay? Okay, and yeah, that is a grams per mole number. And you can look at that in abstractia by itself, again, because that is your molar mass individually, right? Okay, and then yes, I would go ahead and get molar masses together first, because you're going to have your periodic table out. It'll save you time from putting it back out time, right? Yeah. Now, the next thing you are going to do is you're going to do the mole to mole ratio or mole to mole factor, right? And this is, you can think of it like this. These right here the compound formulas, those are what are being accommodated in the molar masses. Okay? So those are what we're dealing with when we're dealing with the molar mass. There's the 2 oxygens for this one, right? That's what we're dealing with there. And then the multimole ratios is how this entire reaction fits together. Okay? And so that's where you go, there's 2 Fe2O3s for every 3 O2s, and that's just the coefficients here. That's all we do, we just plug those over. Okay. Now, if you get very comfortable with this, you can try to do these all in one go. But again, remember, this is going to be like, this one here is about 7 steps to assemble all this all in one go. Okay? And it is easy to get off and forget to add a hydrogen. All right. So the next thing we're going to do is we're going to assemble everything. We start in grams here because that doesn't have anything over it. We're going to be taking that, we're going to be dividing it by the 159.7 grams per mole because we want to get into moles of Fe2O3 and out of grams. The next thing we're going to be doing is we're going to be going ahead and using that mole to mole ratio so we can leave moles of Fe2O3 and get into moles of O2, right? Okay, so we cancel moles of Fe2O3 and we go into moles of O2. All right, so once we're in moles of O2, we just need to get to grams of O2, right? And so we put the moles number on bottom, we put the grams on top, and that gets us into the grams of O2. Okay. Did I lose anybody there? Okay, fantastic. All right. Now again, I would treat these just like my earlier conversions. Okay? That is going to be the easiest way to deal with these things. Treat them like conversions. I'm just converting from one unit to the next, right? And as long as I'm careful with expressing my units each step and I cancel my units out, I'm always going to end up in the correct answer. Okay. All right. So the reaction between H2 and O2, this produces 13.1 grams of water. How many grams of O2 are reacted? So in this case, we're actually using a reactant to go to another reactant, aren't we? Kind of like you figuring out, I have this many cups of sugar, how many cups of flour would I need? I have this many hot dogs, how many buns do I need? Okay. All right, so our grams of water here, first thing we need to do is we need to do what? Yeah, molar mass of water, right? Yeah. And then what's the next step? The mole to mole ratio? Okay, yep, mole to mole ratio, that'd be great. And so, again, we have grams of water here. We want O2, and so we're going to be taking that mole to mole ratio of O2 versus water, right? Okay, and then what's the final step here? We want to be in grams of O2, right? Molar mass of O2. Yeah, you got it. Okay. And so, again, we go ahead and get together our conversion factors just because it's easier to make sure I don't mess up if I do all the additions at once, right? And I have my periodic table out already. Okay, my mole to mole ratio, there are 2 moles of H2O for every 1 mole of O2, right? And so it's a 2-to-1 ratio there. The next thing I'm going to do here is I'm going to get my periodic table out, and the grams of H2O for every 1 mole is what? Yeah, so I take oxygen, 16, plus 2 1s, which are hydrogens, and that gives me 18. The next one I'm going to do here is I'm going to go to oxygen. That's 16 each. That's times 2. And so that's 32 total, right? Okay. Now again, it doesn't really matter which way I write these because I can always flip them later when I need to, right? Okay. So I'm going to be taking my 13.1 grams of water. I'm going to put my grams per mole of H2O water. I'm going to put grams on bottom, moles on top, because I want to get into moles. I then use my mole to mole ratio. Water goes on bottom, oxygen goes on top, because I want to get into oxygen, right? Then I'm going to use my molar mass. This time I'm going into grams. So I put my grams of the oxygen on top, my moles on the bottom. Okay. I go ahead and do the math. 13.1 divided by 18.02 divided by 2 times 32, and that gives me 11.6 grams of O2. All right, so thermite reactions. Now, thermite reaction, very high temperature thermite reaction. Anybody heard of thermite reactions before? Used to weld railroad tracks, of course, but they're also used to do things like welding the barrels of tanks together so they can't shoot at you, and also likely cause the Hindenburg to happen. So, what are the conditions for a reaction to occur? Well, they have to collide together, right? Are two things going to react if they're on the opposite sides of a container or room? No, they can't, can they? The other thing that has to happen is the orientation has to be correct. They're not going to be able to form bonds if they aren't oriented so they could form bonds, right? Can I grasp my hands together if they're oriented back to back? It's not going to work, is it? Okay. And so they have to collide, but they have to collide in the correct orientation so that they could grasp, they could bond. The other thing that has to happen is the energy has to be high enough. Now remember that when you're looking at molecules and atoms, they're surrounded by negative charges, right? And those are the electrons. So when a reaction occurs, it actually has to overcome that initial repulsion that's going to happen, okay? And that's one of the reasons, even though you smack the disk, you don't react with it, do you? Nope. That's because you're not overcoming that energy. Okay? I'd be in deep trouble if I did, right? Uh-oh. Reacted with the desk attached. Can't leave now, huh? All right. That's actually called the energy of activation, by the way. It's the energy barrier you have to overcome for the reaction to take place. It's why the gasoline out in the tanks of the cars out there are not all going boom right now, right? They're not overcoming that energy of activation, okay? Okay, so let's talk about an exothermic reaction. Exo meaning outer, right? Thermic meaning heat. So in an exothermic reaction, we're going to expel heat into the surroundings. This would be the case of a combustion, a fire, right? And so one of the products for an exothermic reaction is heat, energy being released. Specifically, exothermic means heat, actually. This right here would actually be the energy diagram for an exothermic reaction. The energy of your reactants is higher than products, and so you expel heat. Now, note that exothermic reactions usually feed that heat back in so it can overcome the barriers. This right here is actually that activation energy, that energy that you have to overcome for the reaction to happen. Okay? And that's why you can take a match to gasoline and it'll burst into flames, and it'll keep burning. That's an exothermic reaction. Endothermic reactions. You actually don't experience that many endothermic reactions in your life, in your everyday life. An endothermic reaction is actually going to be things like, anybody taken one of those packets that you can break and then it cools itself? Yeah, that's actually an endothermic reaction, okay? It's going to take heat from the surroundings. Another endothermic reaction is actually your sweat going to vapor. That's why that cools you. Or if you want something that's not a bodily fluid, an ice cube, going to liquid water. Also an endothermic reaction. Not very impressive because they stay water, right? Okay. So I guess I'm stopping here. We'll have to push the exam, actually. I'm going to push the exam to Monday, next Monday. We'll finish this up, and that'll be that. Okay? We can't push it anymore. I will have to start probably the next chapter next time. Okay? That won't be on the exam, though. The exam's only going to be, what's the exam cover again? 5, 6, and 7. Very good. Okay, that will get moved. Yeah. Okay. You all have a great day.